Welcome to the debate. Have you ever truly felt the earth spinning beneath your feet? Or maybe questioned why the horizon always looks, well, perfectly flat, even from a really high vantage point? Today, we're diving into one of humanity's most enduring and, frankly, fascinating controversies. It's not necessarily about what the Earth's shape definitively is, although we'll touch on that, but more about how we come to know such fundamental truths about our world. And, why, despite millennia of scientific consensus, the flat Earth model continues to capture public imagination. Our source material presents a really rich array of arguments and models, and I, the advocate, will explore how the robust scientific understanding of a spherical Earth is built upon a foundation of, well, cumulative evidence and inference, which often challenges our immediate sensory perceptions.
And I, the dissenter, will articulate the compelling observations and alternative explanations put forth by proponents of a flat Earth model. We'll delve into their core arguments and worldviews and critically examine the appeal, really, of trusting our direct senses when faced with these complex scientific frameworks. This isn't just about different models of the cosmos, I think. It's about different ways of interpreting reality and authority.
Right. So, when we consider the scientific understanding of Earth's shape, we're looking at a journey that, well, it began with ancient Greek thinkers. Figures like Pythagoras and Aristotle didn't just theorize. Aristophanes, for example, he famously calculated Earth's circumference with remarkable accuracy over 2 millennia ago. He used simple geometry and observations of shadows. It's quite elegant, actually. Fast forward to today, and our understanding is reinforced by countless, easily verifiable phenomena. Think about ships disappearing hull first over the horizon, or the way the last rays of sunlight crawl upwards on tall structures like the Burj Khalifa at sunset. That's a clear demonstration of the sun descending behind a curve, not just sort of receding on a flat plane. The predictable phenomena of polar day and night are also, well, they're impossible on a truly flat surface. Modern technology, from the precision of satellite communication and GPS, which enabled feats like Fyodor Konyukov's solo circumnavigation by balloon, to the consistent eyewitness accounts of astronauts like Sergei Ryazansky directly observing our planet from orbit, all paint a consistent picture of a sphere. These aren't isolated proofs, you see, but a mosaic of evidence, each piece reinforcing the others, alongside experiments that directly demonstrate Earth's curvature and rotation.
Okay, but from the flat Earth perspective, the scientific narrative often asks us to, well, discount what our immediate senses tell us. It urges us to trust complex calculations and remote observations over direct experience. Proponents of a flat Earth, however, they invite us to prioritize that direct experience. They point to the seemingly flat horizon that surrounds us everywhere, and the absence of any felt motion or curvature during everyday life or even long-distance travel. This directly challenges the idea that we are, quote, flying on a sphere. Their primary model depicts Earth as a vast 40,000-kilometer disk with the North Pole at its center, encircled by an immense guarded Antarctic ice wall. Above this disk, the sun and moon are described as rotating in a spiral beneath a celestial dome. Night in this model results from their distance and position, rather than their setting below a curved horizon. These arguments often extend to claims that space travel, satellite images, and even the fundamental concept of gravity itself are an elaborate hoax, orchestrated by organizations like NASA for, financial gain and societal control. They sometimes echo the sentiment that NASA, in Hebrew, through a particular, maybe questionable interpretation, means to deceive. This isn't just a different model, it's a different epistemology, a fundamentally different way of knowing.
That's a powerful point about immediate perception, and it brings us right to the core of this debate. How reliable are our senses when contemplating planetary scale, especially when they often seem to contradict scientific models that offer deeper, predictive understanding? Many flat Earth proponents, figures like the Russian musician Yuri Loza and Andrei Velikanov, argue precisely this, that we should primarily trust what we see, a flat horizon and a stable, unmoving Earth. They often cite historical experiments like Samuel Robothm's 1838 observation on the Bedford Level. There, a boat reportedly remained visible for 10 kilometers over a stretch of water that, by spherical calculations should have been significantly obscured by curvature. And they frequently ask, well, why, if Earth is constantly spinning at hundreds of miles an hour, why don't we feel its motion during our everyday lives?
And those are incredibly compelling questions, aren't they? They really speak to a fundamental human desire for tangible, verifiable proof. From a flat Earth perspective, the very fact that we don't feel the Earth spinning or don't see the horizon curve is considered direct evidence. So when you, the advocate, speak of things like atmospheric refraction explaining Rowbotham's experiment, or relative motion for why we don't feel the spin, well, it asks us to accept an explanation that overrides our direct sensation. And this is precisely where the distrust can begin for many people, I think, when the scientific explanation feels less intuitive than what their own eyes or body tell them.
I understand that natural inclination towards direct sensation, I really do. But scientific understanding often explains why our immediate perception can be deceiving on such a grand scale. For instance, the results of the Rowbotham experiment. They're largely attributed to atmospheric refraction or mirages, basically how light bends through layers of air with different temperatures and densities. It creates optical illusions, much like how a distant oasis appears on a hot desert road. It's a known phenomenon. Physicist Kirill Boldarev's reenactment on the Rybinsk reservoir using a powerful objective lens actually directly contradicted Rowbotham's conclusions. He showed a light source on a snowmobile gradually appearing from behind the curve, bottom first, exactly as you'd expect on a sphere. Our inability to feel Earth's rotation, moving at over 1,000 miles an hour at the equator, mind you, is a matter of relative motion.
It's similar to how you don't feel the speed of an airplane once it reaches cruising altitude. Everything within the plane moves with it, including the air inside. The atmosphere is gravitationally bound to the Earth and rotates with it. It's truly mind-boggling when you stop and think about it. We're cruising at hundreds of miles an hour, constantly curving with the Earth, yet our senses tell us we're on a perfectly straight, stable line. It's a fantastic testament to physics at scale. And that observation about the sun's light boundary crawling upwards on tall buildings like the Burj Khalifa at sunset, that's a clear, repeatable visual indicator of Earth's curvature, not merely the sun retreating on some flat surface. Okay, while those explanations for Rowbotham's experiment and relative motion offer a scientific perspective, they don't quite seem to satisfy other anomalies that flat earthers highlight, especially regarding travel and trajectory. If the curvature is so significant, why don't pilots constantly have to, dip the nose of the aircraft to follow Earth's curve during long flights? The source material even mentions this anecdote about a builder's level carried on a 13-hour flight that reportedly showed no deviation, suggesting a flat trajectory. And why do traditional maps show these seemingly circuitous flight paths, say from Moscow to Mexico? It implies a straight line should be possible on a flat plane. Yuri Loza, for example, further posits that rivers like the Volga, with only a 100-meter elevation drop over 2,500 kilometers, well, he argues they couldn't possibly flow on a spherical surface because that drop would be insufficient to overcome the globe's curvature. These are practical, sort of everyday observations that, for many, challenge the standard scientific model.
You raise some compelling questions there that highlight the perceived discrepancy between experience and theory. But physics offers, I think, quite elegant explanations for these phenomena, too. Pilot instructor Dmitry Polovkin illustrates this clearly. An aircraft in level flight is continuously pulled by gravity towards the Earth's center. This naturally maintains an orientation parallel to the curved surface without needing constant manual adjustments from the pilot. The plane is essentially falling around the Earth, in a sense. The sheer scale of our planet means the curvature of the flight path is just imperceptible to passengers inside. As for that triangular flight challenge, which the Flat Earth blogger Flat Out Hero claimed was impossible on a spherical Earth, offering $100,000, I believe, well, it was successfully completed by a professional pilot in a flight simulator. This demonstrates that such routes are indeed feasible on a globe. They align with what we call shortest distance orthodromic lines, or great circle routes. These are the most efficient paths across a sphere, though they might appear curved on a flat map projection. Regarding rivers, The continuous force of gravity acts across the entire surface, causing water to flow downhill relative to that local surface, regardless of the overall planetary curvature. The 100-meter drop of the Volga, while it seems small over such a vast distance, is entirely consistent with gravitational flow on a spherical body. Water is always seeking the lowest point relative to the local gravitational pull.
Right, but even with these sophisticated explanations for natural phenomena, the flat Earth perspective often comes back to a central and, I think, crucial element: the idea of a vast global conspiracy involving NASA and other space agencies. For many flat earthers, this isn't just about scientific models. It's fundamentally about trust and perceived deception. Proponents like Vadim Shagalov suggest that images and videos from space, including those from the International Space Station, are faked, often claiming they're made by Hollywood studios, and that rocket launches are mere theatrics designed to distract from the truth. They'll point to apparent inconsistencies, maybe like alleged manipulation of astronaut Tim Peake's water bubble video, as proof of this deception. They argue that the Antarctic ice wall is guarded, perhaps by NASA or military forces, to prevent discovery of the world's edge, and that the enormous budget for space exploration is simply, well, money laundering on a grand scale. This narrative of a controlled reality is, for them, a powerful lens through which to interpret all scientific claims that might contradict their direct observations.
I have to say, I'm not convinced by that line of reasoning. Because the notion of a global conspiracy, while it has a certain powerful narrative appeal, it really struggles against an overwhelming and diverse body of evidence, and frankly, against the practical realities of maintaining such a deception. Astronauts like Sergei Ryazanskiy, who has flown on the ISS twice, directly confirm seeing Earth's spherical shape from orbit. He describes it as an undeniable reality, even despite the limited view from 400 kilometers up. Cosmonaut Mikhail Kornienko, who flew with Tim Peake, readily explains the technical setups used for experiments on the ISS. He refutes those fake video claims, like the water bubble one, by simply detailing the science and engineering involved. And crucially, modern society relies heavily on technologies like GPS and satellite communication. These fundamentally operate on the principle of a spherical Earth and a functioning space environment. Fyodor Konyukov's solo circumnavigation by balloon enabled by GPS is a testament to this, as are the millions, billions, perhaps, of daily uses of GPS globally. Furthermore, the sheer number of individuals and nations involved in space exploration and related technologies collaborating across cultures and political divides would make such a widespread long-term deception practically impossible to maintain without a single credible leak or expose over decades. And the idea that NASA in Hebrew means to deceive, that's really a linguistic distortion used to support a narrative. NASA is an English acronym, and the Hebrew word often cited, nasa, has different meanings and no direct etymological link to the agency itself. The scientific framework, while complex, offers a consistent and globally verifiable model, not some kind of secret narrative.
So, this exploration of flat Earth and spherical Earth models, it really highlights the deep tension between, on the one hand, immediate sensory experience, and on the other, rigorous scientific inquiry, and how each approach builds its own internally coherent worldview. Proponents of a flat Earth, from Yuri Loza to Andrei Velikanov, often ground their arguments in what they directly observe: a seemingly flat horizon, no sensation of movement, and the perceived simplicity, maybe, of a disk world. Their model offers a specific cosmology: a guarded Antarctic ice wall, an overhead dome where the sun and moon spiral, and, importantly, a narrative of global conspiracy involving agencies like NASA to explain away conflicting evidence. They view space exploration as a theatrical hoax. It's a powerful appeal to, let's call it, common sense, even if it drastically redefines what common sense truly entails.
And while those are indeed the arguments and models presented by flat Earth proponents, the scientific consensus for a spherical Earth is supported by, well, a rich tapestry of historical evidence, repeatable experiments like Kirill Boldyev's reenactment we discussed, the predictability of natural phenomena like weather patterns and polar day and night, and the advanced capabilities of space-based technology which has enabled everything from precise navigation to global communication and incredible circumnavigation feats like Fyodor Konyukov's. Astronauts like Sergei Ryazanskiy and cosmonauts like Mikhail Kornienko provide direct, first-hand accounts that consistently confirm a spherical planet. These accounts reinforce centuries of scientific observation and measurement, often by revealing phenomena simply invisible to our immediate ground-level perception.
The persistence of flat Earth ideas, though, despite the scientific consensus, it really highlights the complex ways in which individuals interpret evidence, question authority, and ultimately seek meaning. It shows how profoundly our initial assumptions can shape what we consider proof, often leading to alternative worldviews even when faced with widely accepted scientific facts. This exploration, though it seems binary in its models, flat versus sphere, truly deepens our appreciation, I think, for the diverse perspectives that can emerge when considering fundamental questions about our world. It invites further investigation into the nature of scientific proof and belief itself.
Absolutely. It serves as a powerful reminder, really, that understanding the strongest arguments from different sides, not just what they argue, but how they construct their arguments and what underlying assumptions they make, illuminates the material in new and often unexpected ways. Even on a topic as seemingly settled as the Earth's shape, this intellectual exercise underscores the importance of critical thinking in evaluating both direct observation and complex scientific explanation. There is always more to explore and understand in how we perceive and explain the world around us, and how different models can fundamentally shape our entire worldview.